Welcome. In this video, we're going to begin a new topic. We're going to start on sequences. And sequences are going to help us to eventually understand something called a series. And series have really important applications in mathematics. There are numbers that can be written as a series, and there are functions that can be represented as a series. So before we can start working with series, however, we need to learn sequences, and we need to understand what a sequence is and how to write it and rewrite it in different forms. So let's start with a warm-up. Below are a few sequences. See if you can figure out the next three terms of each sequence. So first we have 2, 4, 6, 8. What do you think comes next? 10, 12, 14. Clearly we're just counting up even numbers: 2, 4, 6, 8, 10, 12, 14. Let's look at part B. Negative 1, 1. Negative 1, 1. What's next in this sequence? Well, the pattern goes negative, positive, negative, positive. So our next value should be a negative 1, then a 1, then a negative 1. All right, let's keep going. For part C, we have 1/2, 2/3, 3/4, 4/5. Said another way, we have 1/2, 2/3, 3/4, 4/5, and what comes next? 5/6. Then 6/7, and 7/8. All right, let's take a look at part D. So part D looks a little bit different. So I think we can actually even answer this part here. How is part D different from parts A, B, and C while we're still working on the next three terms of this sequence? So if you notice, for parts A, B, and C, we're given an explicit pattern of numbers, and we just have to find that pattern and then continue the pattern. Here we're given a formula, and we're given 3 blanks. So we have to use this formula to determine what comes first, second, and third. So let's figure out the next 3 terms, which is actually the first 3 terms of part D. So if we let n equal 1, we have 2 times 1 over 1 plus 1. And that's just going to give us 1. If we let n equal 2, we have 2 times 2 over 2 plus 1, which is just 4/3. Finally, if we let n equal 3, we have 2 times 3 over 3 plus 1, which is 6/4, and that reduces to 3/2. Now, can you come up with a formula for the nth term of the sequences in parts A, B, and C? So for part A, we're counting up even numbers, and an even number is any integer multiplied by 2. So our formula for A is 2 to the n, and n starts at 1 and goes to infinity. And for all these cases, I should add n is a positive integer, though I could have just said n is an integer since I'm always going to start with 1 here. So I'm kind of being a little bit redundant, but that's okay. So for part B, we have -1, then 1, then -1, and 1. So we're going back and forth between positive and negatives. So that usually occurs when you have -1 to a power. And if we start with n equals 1, we'll end up with a -1. For n equals 2, we'll end up with positive, n equals 3, negative, and so on, off to infinity. For part C, we have fractions. How are are these fractions changing? For our first term, we have a 1 in the numerator. For our second term, we have a 2 in the numerator. For our third term, we have a 3 in the numerator. And so on. You notice the fourth term has a 4 in the numerator. So clearly, 1, 2, 3, 4, 5, 6, 7, the numerator is always the nth term. So I'm going to have n divided by something. But divided by what? Well, for the first term, I have 2, and 2 equals 1 plus 1. For the second term, we have a 3 in the denominator, and 3 equals 2 plus 1. So second term plus 1. Let's do one more. For the third term, we have a 4 in our denominator, and 4 is equal to 3 plus 1. So if you notice, it's always the nth plus 1 in the denominator. An infinite sequence. So what you just saw above, these patterns of numbers, are infinite sequences. And infinite sequences are simply an ordered list of numbers in this form. So they're going to look like A1, A2, A3, and so on, all the way to the nth term. The subscript n is called the index variable of the sequence, and each an is a term of the sequence. If the sequence can be defined by an explicit formula, then a sub n equals f of n for some function f of n defined over positive integers. So again, positive integers would be 1, 2, 3, 4, and so on. Some sequences can be defined recursively. In this case, one or more of the terms are given. Subsequent terms are defined using earlier terms of the sequence. This is also called a recurrence relation. Probably the most famous recursive sequence is the Fibonacci sequence, and it's defined as follows. So we say the first term, a1, equals 1. The second term also equals 1. And then the nth term equals the immediately preceding term. So if we're on the third term, we'd start with the second term. And it's denoted by a sub n minus 1. And then we add 2 terms back, so a sub n minus 2. And this definition is for any integer greater than or equal to 3. So we can list a few terms out this way, 1, 1. For the third term, we use the formula, and we add 1 plus 1 to get 2. For the fourth term, we add the 2 previous terms, so we add 1 plus 2 to get 3. 3 plus 2 to get 5. 5 plus 3 to get 8. 8 plus 5 to get 13, and so on.